Picture a dining room in Bristol, England, in the early 1900s. The room is immaculate, heavy with dark, oppressive Edwardian furniture. You can hear the rhythmic ticking of a grandfather clock in the hallway, the sharp clinking of silverware against porcelain, but otherwise, the silence inside this room is absolutely suffocating. At the table sits a father and his young son, eating a meal completely alone. The mother, the older brother, the younger sister. They have essentially been banished, forced to eat their meals out in the kitchen. In this formal dining room, there is only one rule, and it is enforced with terrifying, unwavering rigidity by the father. The young boy is only allowed to speak to him in flawless, grammatically perfect French. If the boy makes a mistake, a wrong verb conjugation, a slipped accent, he is violently punished. If he cannot find the exact, precise word to express his thought, he is forced to sit there and say nothing at all, day after day, year after year. To avoid the punishment and the anxiety of this impossible standard, the boy chooses to stop speaking almost entirely. He retreats into a fortress of absolute silence. It was a domestic prison, designed by a tyrant to completely extinguish a child's spirit, molding him into a perfectly obedient automaton. Yet, here is the miraculous, defining twist to the story. This virtually mute boy, a child who became so withdrawn that his future colleagues at Cambridge University would jokingly invent a unit of measurement based on his name, the Dirac, defined as a rate of exactly one word spoken per hour, would grow up to literally rewrite the laws of the universe. He would mathematically predict a completely invisible theoretical concept, antimatter, years before anyone on Earth could build a machine capable of proving it existed. Before we unlock the tragic and beautiful mind of the greatest theoretical physicist since Isaac Newton, welcome to Legendary Lives Unveiled. If you are drawn to the hidden shadows and untold sacrifices that forge the titans of history, please leave a like, share this narrative, and subscribe. We are looking at a mind that learned to see the universe not in words, not in the messy, ambiguous language that humans use to lie to each other or punish each other, but in geometry, in algebra, in the untouchable, perfect language of numbers. If you ask the average person to name a famous physicist, they will say Albert Einstein, or Stephen Hawking, maybe J. Robert Oppenheimer, or Richard Feynman. They rarely say Paul Adrian Maurice Dirac. Today, drawing from Graham Farmello's definitive biography, The Strangest Man, alongside historical records from the early 20th century, incredibly dense academic papers on quantum epistemology, and intensely personal, heartbreaking letters, we are uncovering the deeply contradictory life of Paul Dirac. This is a psychological mystery. We will explore how profound childhood trauma, bizarre personal quirks, and a literal mindedness that bordered on the alien somehow created the foundational architecture of our modern quantum age. To understand how Paul Dirac unlocked the secrets of the universe, we must return to that silent house in Bristol and look at the architect of that silence, his father, Charles Dirac. Charles was a Swiss immigrant who held the position of head of modern languages at the Merchant Venturers Technical College in Bristol. Paul's mother, Florence, was a Cornish librarian. On paper, to the outside world, this looked like a perfectly respectable, educated, middle-class Edwardian upbringing. But behind closed doors, Charles was an absolute tyrant. He ran his household with a level of authoritarian control that is genuinely hard to comprehend today. It was a total domination of his family's daily existence, manifesting most intensely at the dinner table. Charles weaponized the dining room by mandating that Paul only speak in his native French and physically separating him from his mother and siblings. He placed an immense cognitive load on the child. Human language is already full of ambiguity, nuance, emotion, and idiom. Faced with the constant threat of punishment for being imprecise, Paul opted out. If he couldn't formulate a sentence with flawless precision in his head before opening his mouth, he simply wouldn't speak. He spent his critical formative years actively avoiding the ambiguity of human interaction. He didn't learn the social dance of conversation, the give and take, the white lies, the emotional signaling, because math doesn't have the messy emotional baggage of English or French. An equation is perfectly balanced. A geometric proof doesn't lie. It doesn't change its meaning depending on its mood, and it certainly doesn't punish you for using the wrong tone of voice. Math became his absolute sanctuary. But the tragedy of the Dirac household was not just Paul's isolation. We must speak of the dark, heavy shadow that hangs over his early life. His older brother, Felix. Felix bore the brunt of Charles's bullying in a very different way. Outgoing and sensitive, Felix desperately wanted to study medicine, even wishing to join the St. John Ambulance Brigade to help people. But Charles, driven by an incredibly rigid, pragmatic, cynical worldview, absolutely forbade it. He forced Felix to study engineering instead, believing it was a more secure path to a paying job, completely stripping the boy of his autonomy. Without Paul's escape hatch of silent mathematics, Felix was deeply depressed, struggling academically in a field he hated, and completely crushed under his father's domineering will. In March 1925, it reached a breaking point. Felix committed suicide. The local Bristol paper covered it with lurid, sensationalized details, describing the discovery of the dead boy by the bushes. It shattered whatever fragile structure the family had left. Yet, Paul Dirac's reaction to his brother's suicide is one of the most chilling, revealing moments in the historical record. Years later, reflecting on the aftermath and his parents' profound grief, Dirac stated, "I didn't know they cared so much. I never knew that parents were supposed to care for their children, but from then on, I knew." He was in his early 20s, and until that moment of catastrophic tragedy, he genuinely did not understand the concept of parental love. He thought parents were merely authority figures, placed there to enforce rules, administer discipline, and provide food. He had never witnessed unconditional love. This is why, when Charles Dirac finally died a decade later in 1936, Paul wrote a letter to his own wife with a single, coldly factual observation. "I feel much freer now. No grief, no mourning. Just relief that the warden of his childhood prison was permanently gone." Did this severe emotional abuse actually create his genius? Graham Farmello's biography presents a very strong argument that the trauma and the genius are inextricably linked. Growing up in a chaotic, loveless environment where human connection brings only pain and punishment, the brain desperately seeks order. Dirac found that perfect, untouchable order in mathematical physics. He replaced the dangerous reality of his home life with the perfect, safe reality of numbers, obsessively searching for what he called mathematical beauty. Because of his father's insistence on practical skills, Paul attended the Merchant Venturers Technical College rather than an elite British boarding school. There, he took intensive classes in technical drawing and projective geometry. He learned fundamentally spatial thinking, how to visualize complex three-dimensional objects in his mind and map physical reality onto a flat, two-dimensional piece of paper with absolute precision. He was building a 3D rendering engine in his brain. Later in life, when brilliant physicists struggled with clunky, impenetrable algebraic formulas, Dirac simply visualized the geometry of the quantum world in his head. This intense need for logical order gave him an almost superhuman toolkit for understanding the universe. Following his father's dictates, Dirac graduated with a degree in electrical engineering from the University of Bristol in 1921 with first-class honors. But the post-World War I economic depression had left the UK economy in absolute shambles. Millions of soldiers had returned, and jobs were scarce. Dirac applied for a placement at an engineering works in Rugby, but couldn't secure permanent employment. The man whose mind would invent antimatter sat at a tiny desk in his childhood bedroom, meticulously filling out job applications for tractor factories and municipal electrical grids, getting rejection letter after rejection letter. Unable to find work, he hid in academia, securing a small grant to study mathematics at Bristol for 2 more years. Finally, in 1923, the escape hatch opened, a scholarship to St. John's College, Cambridge, to do a PhD in mathematics. He escaped the gravity of Charles Dirac's house and was assigned to a supervisor named Ralph Fowler, a big, burly, highly connected physicist who was the exact opposite of Dirac. Through Fowler, Dirac was thrown headfirst into the birth of quantum mechanics, a time of existential panic for theoretical physics. Physics was suffering from a violent split personality. On one hand, Albert Einstein's special theory of relativity beautifully described the macro world of things moving near the speed of light, showing space and time as a continuous fabric. On the other hand, the brilliant, chaotic minds of Niels Bohr, Werner Heisenberg, and Erwin Schrödinger were championing the new, messy, non-intuitive world of quantum mechanics. In the micro world, energy wasn't continuous. It came in chunky packets, or quanta. Electrons jumped instantaneously in a world of probabilities. They were 2 separate instruction manuals for the universe. But if you tried to put them together, to calculate a single atom moving at the speed of light, the math completely self-destructed. They were mathematically incompatible. In 1925, Dirac obtained an early proof copy of Werner Heisenberg's foundational paper, sent by Ralph Fowler. Heisenberg had figured out that in the quantum world, multiplying complex data tables resulted in math that defied basic logic. A times B is not equal to B times A. In quantum mechanics, the order of measurement changes the outcome, a concept Heisenberg was deeply troubled by. While on vacation in Bristol, taking one of his famous solitary Sunday walks in the countryside, Dirac's spatial geometric brain chewed on the problem, and he had an absolute epiphany. He realized Heisenberg's weird rule wasn't a mistake. It perfectly mirrored an obscure, elegant piece of 19th century classical mechanics developed by the French mathematician Siméon Denis Poisson, known as Poisson brackets. Dirac saw the bridge. He realized the bizarre quantum rules were a beautiful extension of classical physics. He found the translation key, snapping messy, confusing data into a stunningly beautiful, pre-existing mathematical framework overnight. He was only 23 years old, but the quiet, damaged boy from Bristol was only warming up. For his next act, he wouldn't just solve a peer's problem. He would attempt to rewrite the ultimate code of the universe, bridging a mathematical impossibility that had paralyzed the greatest minds on Earth. 3 years later, in 1928, Dirac decides to tackle the big one. He wants to solve the impossible task, to unify Einstein's relativity with quantum mechanics. He wants to write the ultimate equation for the relativistic electron. Earlier attempts, like a famous one called the Klein-Gordon equation, had tried to use Einstein's energy equation directly. Einstein's relativistic energy equation is essentially the Pythagorean theorem on steroids. It uses squared terms. For the physics nerds listening, the full, unshortened version of the famous E equals mc squared is actually E squared equals m squared c to the power of 4 plus p squared c squared. Because it fundamentally relies on squared terms, when you try to turn that equation into a quantum wave function, it requires taking second derivatives with respect to time. Here is the fatal flaw. The rules of quantum mechanics dictate that to predict the future state of a particle, you need an equation that only has a first derivative with respect to time. The equation has to be linear. If you use second derivatives, the math spits out negative probabilities. You end up with a negative 30% chance of finding an electron, which is physically meaningless nonsense. Mathematically speaking, Dirac needs to figure out how to take the square root of Einstein's equation. He needs to unsquare the energy and the momentum to get back to a linear first derivative state. But anyone who remembers high school algebra knows why that is a nightmare. You cannot simply say that the square root of a squared plus b squared is a plus b. If you multiply a plus b times a plus b, you get a squared plus 2ab plus b squared. You have that extra, messy 2ab sitting in the middle. Those cross terms completely ruin the clean square root. That is the exact mathematical wall that stopped every genius in the world in their tracks. How do you take the square root of a sum of squares without generating those messy middle cross terms? Dirac needed to find a way to make those cross terms magically cancel out to zero. He needed to invent mysterious mathematical objects. Let's call them alphas, where alpha 1 times alpha 2 plus alpha 2 times alpha 1 equals 0. In mathematical terms, they had to anti-commute. But regular numbers don't do that. 5 times 6 plus 6 times 5 equals 60. It is never 0. So Dirac sat at his desk, staring into the fire in his room at St. John's College, completely ignoring the physical reality of electrons and focusing purely on the logical demands of the math. He realized regular numbers wouldn't work. He tried using 2x2 matrices, small grids of numbers that the brilliant physicist Wolfgang Pauli had used recently. But they weren't big enough. They couldn't hold all the necessary dimensions of space and time, driven purely by the aesthetic need to make the equation work. Dirac realized he had to use larger grids. He had to use 4x4 matrices. It is as if he was trying to crack a safe, and a normal lock with a single numbered dial wouldn't work. Even a lock with 2 dials wouldn't work. So he realizes he needs a lock with 4 interconnected dials that spin in extra dimensions. He essentially invents a new mathematical alphabet just to make the equation balance. He constructed a set of 4 different 4x4 matrices that fit his bizarre criteria perfectly. He didn't know it at the time, but he had actually independently rediscovered a forgotten branch of 19th century mathematics called Clifford algebra. By inserting these specific matrices into his equation, a mathematical miracle occurred. The cross terms, the messy 2ab parts, completely vanished. The square root was perfectly clean, the equation was linear. It obeyed quantum mechanics, and it obeyed relativity. It was mathematically beautiful. He had formulated the Dirac equation. This elegant, compact equation successfully married the macro world and the micro world for the first time in history. It is considered one of the greatest achievements of the human intellect. In fact, that specific equation is carved into the ancient stone floor of Westminster Abbey today. But here is the part of the story that still gives physicists chills: the unintended consequences. Because Dirac used 4x4 matrices to make the math work, the wave function representing the electron couldn't just be a single simple number anymore. To interact mathematically with a 4x4 matrix, the wave function had to be a vector with 4 distinct components, known today as a Dirac spinor. The math forced him to describe the electron not as a single point, but as a complex entity with 4 distinct mathematical attributes. What do they represent in the real world? Dirac had absolutely no idea at first. He just did it because the algebra demanded it, completely unfazed by what it meant in physical reality. But when other physicists analyzed these 4 components, they realized the math was trying to tell them a profound secret about the universe. 2 of those 4 components perfectly, naturally described a mysterious phenomenon called electron spin. In the 1920s, experimental physicists were noticing that electrons behaved like tiny magnets, as if they were spinning on an axis creating a magnetic field, but nobody could explain why. It was just a weird anomaly in the lab data. Dirac did not set out to explain electron spin. He didn't build his equation by looking at that lab data and reverse engineering a formula to fit the magnetism. Spin simply fell out of his math automatically. It was a mandatory consequence of combining relativity and quantum mechanics. The equation demanded that spin exist. It was as if the mathematics was smarter than the man who wrote it. He trusted the pure abstract geometry so completely that he let it lead him to a hidden physical reality. He let the math dictate the physics, but mathematical perfection comes with a very dangerous price. When you blindly trust the math, it sometimes spits out impossible answers. Those other two components of his four-component wave function were about to cause a massive crisis. The problem goes back to that quadratic nature of Einstein's original energy equation. Think back to basic high school algebra. If x squared equals 4, what is x? It could be 2, or it could be minus 2, because minus 2 times minus 2 is also positive 4. The square root always has a positive solution and a negative solution. When Dirac finally solved his beautiful new linear equation, it yielded solutions for electrons with positive energy, which is completely normal. That is everything we observe in the physical world around us. But it also unavoidably yielded solutions for electrons with negative energy. In classical physics, if an equation gave you a negative result for something like energy or mass, you would just throw that negative solution in the garbage. You'd say that is unphysical, just a mathematical artifact of the square root. It's like an equation telling you a train is traveling at negative 50 miles per hour. You ignore the philosophical implications of the minus sign, apply common sense, and ignore the weird math. But you cannot do that in quantum mechanics. The quantum world is dynamic. Particles are constantly transitioning between available energy states, emitting or absorbing photons as they jump around. If mathematically valid negative energy states truly exist in the universe, an electron with positive energy should naturally want to fall down into a lower energy state. Like a boulder rolling down a hill, an electron would drop from positive energy past zero and cascade down into an infinite, bottomless pit of negative energy levels. The ultimate consequence of Dirac's equation was that every electron in the universe should instantaneously fall into this negative abyss, releasing an infinite burst of light, and all matter in the universe would collapse in a fraction of a second. It was a glaring, fatal flaw. The greatest physicists in the world, including Werner Heisenberg, looked at this result and said it was obviously broken. Reality doesn't collapse, but Dirac refuses to throw the equation out. He is so utterly dogmatically convinced of its mathematical beauty that he decides the equation isn't wrong. He decides that reality must simply be weirder than anyone ever imagined. To save his beautiful equation, in 1930, Dirac proposes a hypothesis so radical, it sounded like a joke. He looks at this infinite abyss of negative energy states that threatens to swallow the universe, and he says, what if those negative energy states aren't empty? What if they are already completely full? Dirac hypothesized that the entire vacuum of space, every single inch of the universe that we think of as empty, the void between stars, the empty space in this room, is actually an infinite, invisible, bottomless ocean of negative energy electrons. It became known as the Dirac Sea. Electrons obey a fundamental rule called the Pauli exclusion principle, which dictates that no two electrons can occupy the exact same quantum state at the same time, like seats in a movie theater. So if the infinite Dirac sea of negative energy is completely full, every single seat is taken, then the positive energy electrons we see in our everyday world cannot fall down into the negative energy abyss. The universe doesn't collapse because there is no room for the electrons to fall into. The sea is full. From an empirical scientific standpoint, it sounded like absolute madness. He essentially got a math result, implying negative apples. And instead of assuming a typo, he confidently declared that the entire vacuum of space must be made of an infinite, undetectable ocean of anti-apples. It violates Occam's razor entirely. The physics community mocked him relentlessly. Niels Bohr, the great patriarch of quantum mechanics, joked that Dirac's theory was a fantastic way to catch an elephant. You just put up a poster explaining the Dirac Sea by a watering hole in Africa. The elephant walks up, reads the poster, gets so intensely confused and stunned by how ridiculous the theory is that you can casually tie it up. Wolfgang Pauli was equally dismissive, calling it mystical, untestable nonsense. But Dirac isn't done. He asks a theoretical question. What happens if you shoot enough energy, say a highly energetic cosmic ray photon, into this invisible sea? You could theoretically hit one of those invisible negative energy electrons so hard that you knock it completely out of the sea and up into our positive energy world. It is like taking a bucket and scooping a cup of water out of the surface of the ocean. You are left with two distinct things. First, the water you scooped out appears in our world as a normal, positively energized, negatively charged electron. But second, you are left with a hole in the sea, an empty bubble in an infinite, completely uniform background of negative charge. The absence of the negative acts exactly like a localized positive charge. Like a bubble in water moving upward, acting as if it has anti-gravity. Dirac theorized that this hole would behave mathematically and physically like a completely new, unseen particle. It would have the exact same mass as a normal electron, but it would have a positive charge instead of a negative one. He predicted antimatter. By 1931, brushing off all the mockery, he explicitly published a paper predicting the existence of the anti-electron. He went even further, stating that every fundamental particle in the universe must have a corresponding antiparticle. He literally doubled the amount of matter in the universe using nothing but a pencil, a piece of paper, and an unwavering faith in the aesthetic beauty of his matrices. And people were still laughing. Right up until the summer of 1932, that is when a young experimental physicist in California named Carl Anderson was studying cosmic rays hitting the Earth from deep space. Anderson was using a cloud chamber surrounded by a strong magnetic field. He photographed a particle track condensing in the chamber. The track showed a particle that had the exact tiny mass of an electron, but it curved in the magnetic field in the wrong direction, the way a positively charged particle would curve. Anderson didn't know anything about Dirac's crazy theory. He just looked at the data. He had discovered the positron. The anti-electron was real. The laughter stopped completely, instantly. The discovery undeniably vindicated Dirac's crazy mathematical leap of faith. The holes in the sea were real particles raining down from the sky. It was a triumph of theoretical physics, unlike almost anything in history. Up until then, physicists discovered things in a lab, and then mathematicians wrote equations to explain them. Dirac wrote an equation, and the equation told the experimentalists what to go look for in the lab. As a result, in 1933, at the incredibly young age of 31, Paul Dirac was awarded the Nobel Prize in Physics, sharing it with Erwin Schrödinger. This isn't just abstract blackboard theory anymore. This is applied medicine today. If you or a family member has ever had a PET scan at a hospital to detect cancer, you are experiencing the direct application of his theory. PET stands for positron emission tomography. They inject a radioactive tracer into your bloodstream, and as it decays, it literally emits Dirac's impossible antimatter inside your body. Those positrons travel a fraction of a millimeter before they hit the normal electrons in your tissue. They violently annihilate each other, dropping back into the Dirac sea. And that tiny explosion of gamma rays is what the machine reads to create a high-resolution image. We are literally using the Dirac sea to find tumors. But if we connect this breathtaking victory to the psychological profile we built earlier, you can see how this triumph set a trap for him. It solidified Dirac's core, fundamental belief system. He had trusted the pure beauty of his mathematics over common sense, over empirical evidence, over the mockery of his peers, and he had won the Nobel Prize for it. His coping mechanism for his childhood trauma had just unlocked the universe, but that absolute validation, it calcified his thinking. His reliance on mathematical beauty was no longer just a strategy. It became an unshakable dogma, a religion that would eventually, tragically alienate him from the very scientific community he had just helped build. Let us speak of a philosophical conflict, a religion of mathematical beauty versus the messy, ugly reality of experimental data. Because Paul Dirac didn't just casually prefer nice-looking equations. He stated it as a fundamental, non-negotiable law of nature. In a famous article he wrote for Scientific American in 1963, he laid out his doctrine clearly. A theory with mathematical beauty is more likely to be correct than an ugly one that fits some experimental data. This is a massive epistemological debate. The foundational premise of the scientific method, since Galileo and Bacon, is that experiment dictates reality. If your elegant theory doesn't match the data coming out of the laboratory, your theory is wrong. But to understand Dirac, you must look through his almost Platonic lens. Dirac believed that human experiments are inherently flawed. Our machines are imperfect, our physical senses are limited, and our data is tainted by environmental noise. Mathematics, however, is eternal. He famously wrote, "God is a mathematician of a very high order, and he used very advanced mathematics to construct the universe." He meant a Spinozan God. He viewed mathematics not as a human invention, but as the literal objective blueprint of reality. This rigid dogma became a massive, career-ending problem for Dirac after World War II. During the late 1940s and 1950s, the next generation of theoretical physicists, brilliant, pragmatic minds like Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, were trying to advance a field called quantum electrodynamics, or QED. They were calculating the complex interactions between electrons and photons, but they ran into a wall. The equations kept catastrophically breaking down, repeatedly spitting out infinity as the answer for basic physical properties, like the mass or the charge of an electron. To solve this, Richard Feynman, Julian Schwinger, and Shinichiro Tominaga developed a complex mathematical technique called renormalization. It was a way of mathematically packaging up those messy infinities, isolating them, and then systematically canceling them out by inserting empirical measured values taken directly from laboratory experiments. It worked brilliantly, predicting the magnetic moment of the electron matching experimental data to something like 10 decimal places, earning them the Nobel Prize. But Paul Dirac absolutely despised it. He rejected the most successful theory in history, calling renormalization an abomination and a stopgap procedure. He said it was just a set of arbitrary, illogical, working rules that completely lacked foundational mathematical rigor or elegance. It was a messy, pragmatic hack that offended his deeply ingrained need for perfect order. Because of this uncompromising aesthetic dogma, Dirac spent decades of his life completely isolated from the mainstream physics community. The historian of physics Helge Krag noted that the mid-1930s marked a major, tragic dividing line in Dirac's career. After explicitly adopting this principle, his productivity in lasting physics basically ended. In the 1970s, when his old friend Werner Heisenberg sent him a manuscript of a new unified theory, Dirac replied with a single, devastating line: "The equations are so ugly, it cannot possibly be right." The very survival mechanism he developed as a child became his fatal flaw. This absolute rigidity governed how he navigated his daily life. Niels Bohr famously called him the strangest man, which biographer Graham Farmelo used for the title of his book. Dirac's extreme taciturnity, which led to the joke of the Dirac unit of 1 word per hour, was a fundamental refusal to participate in the messy ambiguity of conversational language. At a major physics conference, after Dirac filled a blackboard with dense equations, a respected colleague stated, "Professor Dirac, I don't understand the equation on the top right-hand corner of the blackboard." After minutes of unbearable silence, the moderator asked Dirac if he wanted to answer. Dirac, genuinely confused, replied, "That was not a question. It was a comment." He processed language with strict, computer-like literalism, sailing to a physics conference in Japan in 1929 with Werner Heisenberg. Dirac watched his handsome, extroverted colleague dancing with girls in the ship's ballroom. Observing this illogical behavior, Dirac asked, "Why do you dance?" Heisenberg replied, "Well, when there are nice girls, it is a pleasure to dance with them." Dirac thought about this data point for a very long time before asking in all seriousness, "But Heisenberg, how do you know beforehand that the girls are nice?" He loved to joke about a parish priest visiting a woman who had 5 sets of twins. When the priest asks, "My goodness, do you always have twins?" the woman logically replies, "No, Father, sometimes we have nothing." Dirac thought it was the height of humor because it highlighted literal precision. Biographer Graham Farmelo strongly suggests in his book that Paul Dirac was autistic, pointing to his hypersensitivity to sudden sounds, his rigid mind, and his inability to read emotional nuance, even consulting with leading autism experts like Simon Baron-Cohen at Cambridge. But there is a real danger in retroactively diagnosing a historical figure. If we reduce him to an emotionless calculating machine, we risk missing the incredibly deep, hidden humanity inside him. The most heartbreaking proof of this is his relationship with the Dutch physicist Paul Ehrenfest. At the 1933 Solvay conference in Copenhagen, Ehrenfest, the highly social emotional glue of the physics community, was suffering from severe, crippling depression. Dirac saw right through Ehrenfest's pain, taking the time to sit quietly with him and offer profound professional respect and validation. Tragically, it wasn't enough. Shortly after returning to the Netherlands, overwhelmed by despair, Paul Ehrenfest shot his institutionalized son, who had Down syndrome, and then turned the gun on himself. The exact same man who coldly wrote, "I feel much freer now," when his own father died, was completely shattered. Dirac sat down and wrote a 4-page, deeply emotional, handwritten letter to Niels Bohr. Farmelo describes this letter as having the fluency of a novelist and an incredible sensitivity to emotional nuance. Dirac wept over the loss, agonizing over the signs they had missed. Later in life, he sobbed uncontrollably when he learned of Albert Einstein's death. He wasn't devoid of empathy. The emotions were there, buried deep beneath mathematical armor. In 1934, while on sabbatical at the Institute for Advanced Study in Princeton, 32-year-old Dirac met Margit Wigner, known to everyone as Mansi. She was the sister of the famous physicist Eugene Wigner, and as a vibrant, extroverted Hungarian divorcee, she was Dirac's exact polar opposite. She pursued him relentlessly. Dirac tried to logically argue his way out of the romance, literally writing to her, "I am not in love with you. As I have never been in love, I cannot understand finer feelings. He even sent her a questionnaire asking her to categorize her feelings. But Mansi simply decided to build an emotional infrastructure for him, and her sheer, unwavering force of will eventually wore down his logic. They were married in London in 1937. His close friend, the brilliant Russian physicist Peter Kapitsa, wrote a letter to Ernest Rutherford saying it makes him much more human. Dirac adopted her 2 children, Gabriel and Judith, and together they had 2 daughters, Mary and Monica. Mansi handled all the social fiction and dinner parties, tethering the silent physicist to the real world while he pursued his beautiful equations. In 1969, after holding the Lucasian professorship for an astonishing 37 years, Dirac reached the mandatory retirement age at Cambridge. He traded the gloomy academic fens for the sunshine of Florida, accepting a professorship at Florida State University in Tallahassee. In his final act, the man who invented antimatter spent his evenings watching Nova Science documentaries, episodes of the British drama Upstairs, Downstairs, and, bizarrely, the Sonny and Cher Comedy Hour. He took walks around the campus, swam in local lakes, and lived as a revered elder statesman. Paul Dirac died peacefully in Tallahassee on October 20th, 1984, at the age of 82, and is buried in Roselawn Cemetery. In 1995, a memorial plaque was finally dedicated to him in Westminster Abbey, right next to the Grand Monument for Sir Isaac Newton. Carved directly into the ancient stone is no flowery epitaph. It is simply the Dirac equation, a perfect testament to a man who believed the deepest truths are written in the pure, eternal beauty of mathematics. Today, right now, thousands of brilliant physicists are searching for the ultimate theory of everything, a single equation that unites the gravity of Albert Einstein with the quantum world of Niels Bohr. They are stuck. But what if Dirac was right all along? Is it possible that the final equation explaining our entire existence hasn't been found simply because the physicists looking for it haven't learned how to think like artists? If you were fascinated by the hidden tragedy and triumph behind the mind of Paul Dirac, make sure you hit that like button, share this with a fellow curious mind, and subscribe to Legendary Lives Unveiled. We bring you the untold, dramatic truths behind history's greatest figures every week. Until next time, remember that silent dining room in Bristol and keep questioning the universe.